Diploma in Electrical Engineering. Switchgear and Protection System. NoteWise Academy. Let's start. Smiling face heart heart.
Unit 2. Short circuit faults. 2.1. Definition, reason and consequence of faults in power system. Answer. In a power system, a fault refers to any abnormal condition that disrupts the normal flow of electrical current. Here's a breakdown of the definition, reasons, and consequences of faults in a power system. Definition of fault. A fault in a power system is any unintended electrical condition that deviates from the normal operating parameters of the system. It can include events such as short circuits, ground faults, open circuits, and insulation failures. Reasons for faults. Faults in a power system can occur due to various reasons, including 1. Equipment failure. Malfunction or breakdown of electrical equipment such as transformers, circuit breakers, cables, and switches can lead to faults in the system. This can be caused by aging, wear and tear, manufacturing defects, or inadequate maintenance. 2. Environmental factors. External factors such as lightning strikes, high winds, ice storms, and animal interference can cause faults by damaging power lines, insulators, and other components of the power system. 4. Natural events. Geological events such as earthquakes, landslides, and floods can cause faults by disrupting underground cables, damaging substations, and affecting the stability of the power grid. Consequences of faults. Faults in a power system can have several consequences, including 1. Power interruptions. Faults can lead to power outages and interruptions, affecting homes, businesses, industries, and critical infrastructure. This can result in inconvenience, financial losses, decreased productivity, and disruption of essential services. 2. Equipment damage. Faults can cause damage to electrical equipment such as transformers, generators, circuit breakers, and cables. This can result in costly repairs, replacement of equipment, and prolonged downtime for maintenance and restoration. 3. Safety hazards. Faults pose safety hazards to personnel working on or around electrical equipment. They can lead to electric shocks, arc flashes, fires, and other accidents that may result in injuries or fatalities. 4. System instability. Faults can destabilize the electrical system, leading to voltage fluctuations, frequency deviations, and system-wide disturbances. This can affect the performance of sensitive equipment, cause cascading failures, and compromise the reliability of the power grid. Overall, faults in a power system are inevitable occurrences that require effective protection measures, proactive maintenance, and emergency response strategies to minimize their impact and ensure the safe, reliable, and efficient operation of the electrical network. 2.2. Concept of short-circuit fault current and fault MVA. Answer. The concept of short-circuit fault current and fault MVA, megavolt amperes, are fundamental in understanding the magnitude of electrical faults and their impact on power systems. Here's a brief explanation of each. 1. Short-circuit fault current. Short-circuit fault current refers to the current that flows when a short circuit occurs in an electrical system. A short circuit fault occurs when there is an unintended low-resistance connection between two conductors, bypassing the normal load. The magnitude of the short-circuit fault current depends on factors such as the voltage level of the system, the impedance of the power sources and transmission lines, and the point of fault location. Short-circuit fault currents can be several times higher than the normal operating currents in the system and can pose significant safety hazards and equipment damage if not properly managed. 2. Fault MVA, megavolt amperes. Fault MVA refers to the magnitude of the fault current expressed in megavolt amperes, which is a unit of apparent power. It represents the product of the voltage and current during a fault condition, typically measured in three-phase systems. Fault MVA is used to quantify the power available during a fault and is essential for determining the rating of protective devices such as circuit breakers, fuses, and relays. Knowing the fault MVA helps engineers design and select appropriate protective devices that can safely interrupt the fault current and isolate the faulty part of the system without causing damage to equipment or compromising system reliability. In summary, short-circuit fault current and fault MVA are critical parameters in assessing the magnitude of electrical faults and ensuring the effective protection and safe operation of power systems. Understanding these concepts is essential for designing, analyzing, and maintaining electrical networks to prevent accidents, minimize downtime, and ensure the reliability of electrical supply. 2.3. Representation of power system for fault calculation. Per unit system, reactance. Diagram and fault calculation. Answer. In power systems, fault calculations are often performed using the per unit system and represented using reactance diagrams. Here's how these concepts are applied in fault calculations. 1. Per unit system. The per unit system is a method of normalizing values in a power system to a common base, making it easier to compare and analyze different components. In the per unit system, all quantities such as voltage, current, power, and impedance are expressed as fractions or percentages of their base values. The base values used in the per unit system are typically chosen to be the rated values of the equipment in the power system, such as the rated voltage and rated power of transformers, generators, and transmission lines. By expressing all quantities in per unit values, fault calculations become simpler, and the results are easier to interpret and apply across different components of the power system. 2. Reactance diagram. A reactance diagram is a graphical representation of the impedance of different components in a power system, typically expressed in per unit values. In a reactance diagram, the reactances of various components such as generators, transformers, transmission lines, and loads are represented by impedance lines. Impedance lines represent both the resistance and reactance of the components and are drawn at an angle corresponding to the power factor of the component. Reactance diagrams help visualize the flow of current and voltage in the power system and are used in fault calculations to determine the impedance seen by a fault at different points in the system. 3. Fault calculation. Fault calculations in power systems involve determining the fault current and voltage under different fault conditions, such as short circuits, ground faults, and open circuits. Using the per unit system and reactance diagrams, fault calculations involve applying Ohm's law and Kirchhoff's laws to calculate the fault current and voltage at various points in the system. The fault current and voltage depend on factors such as the impedance of the components in the system, the location and type of fault, and the operating conditions of the system. Fault calculations help engineers design and select protective devices such as circuit breakers, fuses, and relays to safely isolate faults and protect equipment in the power system. In summary, the per unit system and reactance diagrams are essential tools for representing power systems and performing fault calculations. They simplify the analysis and interpretation of fault conditions and help ensure the safe and reliable operation of electrical networks. 2.4. Short circuit in different sections: generator, bus bar, transmission, distribution lines. And their consequences. Answer. Short circuits can occur in various sections of a power system, including generators, bus bars, and transmission or distribution lines. Here's a breakdown of short circuits in each section and their consequences. 1. Short circuit at generators. A short circuit at a generator can occur due to faults within the generator windings or in the connections between the generator and the rest of the system. Consequences. Mechanical stress. Short circuits can cause mechanical stress on the generator rotor and stator due to the sudden increase in electromagnetic forces. Thermal stress. The high currents associated with short circuits can lead to overheating of generator windings, insulation degradation, and potential damage to the generator. Voltage instability. Short circuits at generators can lead to voltage instability in the power system, affecting the performance of connected loads and other generators. 2. Short circuit at bus bars. A short circuit at a bus bar typically occurs due to faults in the connections between circuit breakers, switches, and other equipment at the bus bar. Consequences. Interruption of power supply. Short circuits at bus bars can lead to the interruption of power supply to connected loads and equipment. Damage to switchgear. Short circuits can cause damage to switchgear and protective devices such as circuit breakers, resulting in downtime for maintenance and repairs. Fire hazard. Short circuits at bus bars can pose a fire hazard due to the high currents and heat generated, especially if proper protective measures are not in place. 3. Short circuit in transmission, distribution lines. Short circuits in transmission or distribution lines can occur due to a variety of reasons, including conductor contact with vegetation, animals, or other objects, as well as insulation failure or conductor damage. Consequences. Power outages. Short circuits in transmission or distribution lines can lead to power outages affecting large areas or specific regions of the power system. Equipment damage. Short circuits can cause damage to transformers, switches, and other equipment connected to the affected lines, leading to costly repairs and replacements. Safety hazards. Short circuits can pose safety hazards to personnel working on or near the affected lines, including electric shock hazards and fire risks. In summary, short circuits in different sections of a power system can have significant consequences, including equipment damage, power outages, safety hazards, and interruptions to power supply. Proper maintenance, inspection, and protection measures are essential to prevent and mitigate the impact of short circuits in power systems.
Thanks for watching. Like, comment, subscribe, and share your friend's zone.